Hi everyone, my name is Rangsati Jason Srinivasa from Easy D section. This subject is linear algebra and calculus. Today I'm telling about TikTok topic. My TikTok topic is a class in invertible circulant matrices for Qc-Ldpc course. Qc-Ldpc means full form is quasi cyclic low density partiality check. Next topic and the second topic in the second topic is circulant matrices notation and properties. And the general structure of an n circular matrix A defined over a definite finite field Galois field GF of P is as follows. A equals to a naught a1 a2 so on an minus 1 and an minus 1 a naught a1 so on an minus 2 and so on a1 a2 a3 so on a naught is considered as the first equation, and where ai belongs to gf of p means Galois field of p, thus it is described by one of its rows, the others being obtained through a cyclic shift by t positions with 1 is less than or equal to t is less than or equal to n minus 1. A 4 length cycle in matrix A is closed rectangular path linked non-zero elements. Explicitly, this means that a four-line cycle exists when two rows have a pair of non-zero symbols at the same position, that is, belonging to the same columns. Obviously, each matrix can have manifold loops of this kind depending on the distribution of the non-zero symbols. It is possible to verify that a four-lane cycle in matrix A do not appear if and only if the distance between any other of non-zero symbols in each row of the matrix are different from each other. So if uh, sigma I comma k represents the distance mod n the between the ith and kth non-zero elements. It must be sigma ik equals to sigma j comma l if and only if I equals to j and k equals to l. Orthogonal matrices are special case of circulant matrix for which A into A transpose equals to I. So the inverse of an orthogonal matrix coincides with its transpose. Let us denote by W of A the matrix weight, that is defined as the number of non-zero symbols in each row of matrix A. The following theorem holds. And the next topic is third topic, unitary circulant matrix. Let us consider n equals to ps with s an integer and the rings rs equals to gf of p of y by y power s minus 1. Let us define the map. Uh, uh, Let us define the map. The equation which is given in this, consider it as a third equation. where the next equation equals to fourth equation. Considered as fourth equation, it is known that is an homo homomorphism, and that Ker is equals to I power Ps to the base s, being the ideal I power Ps to the base s equals to x power s minus 1 belongs to R per Rn, completely described by the following formula. A of x equals to n minus 1, I equals to 0, ai x power I belongs to I power Ps Ia implies p minus I, p minus 1, integration t equals to 0, ak plus ts equals to 0 as the fifth equation, with k equals to 0 comma minus 1, generalizing third uh, generalizing generalizing third equation. We can consider we can consider n equals to p power qs and p power qs, and the map given p power q s to the base p power r s is to r to the base p power q base implies r to the base p power r s, then with 0 less than or equal to or less than or equal to q, and ker equals to I equals to x power p s x power p minus 1, and if r equals to q is the identity map. Afterwards we will consider matrices for which we call them unitary circulant matrices, and we denote by the subset of the matrices in Rp R to the base p power qs for which this property is satisfied. And the fourth one is unitary matrix inversion. For n equals to p power q s, we can observe that if a of x belongs to Rn, then a of x p power r equals to 1 p power q s equals to 1 p 1 to the base p power q minus r base 10 base s, then with 0 is less than r is less than or equal to 0 is less than r less than equal to q. From now on we will set p equals to 2 under the assumption for a matrix A with n equals to 2s, that is q equals to 1, satisfying the condition equals to 1. This implies a power minus 1 of x equals to a of x, then, which means that a coincides a, a coincides with its inverse. This result permits to prove the following, and prove perm a coincides with its inverse. And the fifth topic is 4 length cycle. From fourth equation we derive that to have u naught equals to 1, that implies a belongs to either a naught or as must be different from 0. Based on this evidence we can formulate it. Then seventh one is an next is example. By introducing a unitary block in the parity check matrix, we are able to design Qc-Ldpc codes characterized by space generator matrices that is low encoding complexity. Each Qc-Ldpc code in the proposed family has length n, dimension k, and a parity check matrix H formed by a row H naught so on H n naught minus 1 of n naught space circulant blocks with size z equals to n by n naught. Matrix G is formed by a k by k identity matrix and with k equals to k naught dot z equal and k naught equals to n minus 1 followed by a column of k naught circulant blocks. If we uh, if and the next is this is the figure of the topic. uh, in the graph we have to draw this top mm, image graph. We draw the diagram. In this diagram tells about figure 1 bit error rate BER as BR and frame error rate as FER of a Qc-Ldpc code n equals to 8192 and k equals to 7168 assigned through assigned through um, one second assigned through mm, designed through the proposed technique. Suppose Hn naught minus 1 to be non-singular, G can be obtained as follows. G is a matrix I H power minus H inverse n naught minus 1 dot H naught power whole power transpose H inverse n naught minus 1 dot H1 whole transpose so on H inverse n naught minus 1 dot H naught Hn naught uh, minus 2 whole power t whole transpose from 17 consider it as 17th equation. So now from 17th equation we notice that the density of matrix G depends on that of H inverse n naught minus 1 uh, H inverse to the base n naught minus 1. In general, the inverse of H n naught minus 1 in dense so the right part of G is dense as well. On the contrary of choice, H n naught minus 1 equals to I characteristic of LDGM code produced as the sparsest G but reducing the minimum distance. Our choice instead consists in adopting a unitary block as h to the base n naught minus 1 that has a space inverse without a being neither an identity matrix nor a permutation matrix and is an example for this. And since the conclusion before that conclusion I want to tell some one example. As an example, we have designed a Qc-Ldpc code with n equals to 8192 and k equals to 7168 that are values similar to those proposed uh, those those proposed those proposed for adoption in near Earth space mission missions by Consultative Committee for Space Date Systems CCSDS. The performance achieved shown in figure 1 and is very close to those obtained through more consolidated design approaches, but the proposed solution has the advantage of a space generator matrix. The the considered code for sorry, the the considered code, for example, has a parity check matrix formed by 8 circulant blocks with a size 1024 and row or column weight 5. The circulant block in the right part of GC in equation 17 have row or column weight 75, that is small compared to their size. Hence the conclusion, the proposed class of unitary circulant matrices has great potentialities. Their inversion complexity is determined by the weight and is basically independent of this size, which makes them particularly suitable and processing operation in LDPC code. They permit to design Qc-Ldpc code free of for length cycle and characterized by low density generator matrices. Thank you. I hope you all like my TikTok video. Because of my I think I have done some mistakes in this video, but for the next time onwards I will next time onwards I will not do like this mistakes. Sorry for mistake. Thank you.